Hi, my name is William Gower from emew Corporation. Today we're talking about electronic waste and electronic waste recycling with our technical expert, Dr. Michael Korzenski. Michael, would you like to introduce yourself to our viewers?
Sure. As William said, my name is Michael Korzenski. I'm president and founder of Ortera Consulting, and I'm a technical advisor of sustainable development for emew. My experience and background is focused on green chemistry and engineering and designing cradle-to-cradle processes which use chemicals and chemistry in a manner for metal recovery, but in a manner where we can recoup as much of that chemical back into the process to minimize, and in some cases, eliminate any waste streams, be it liquid, gaseous, or solid.
And just quickly, Michael, approximately, how long have you been doing this? In terms of your expertise.
In the area of chemistry, about 25 years. On the area specifically focused on electronic waste, around 14 to 15 years now.
So, yeah, an extensive amount of experience. Michael, recently we caught an article from market research which talked a little bit about, global metal recycling trends, et cetera, et cetera. In 2019, the estimates for the market for metal recycling was approximately 55 billion dollars in 2019, and that's expected to grow to over 88.5 billion dollars by 2027. It's an enormous amount of money. What sort of metals are we talking about that sort of are sort of in that forecast? Are we talking simple base metals? Are we talking exotic stuff? I mean, any comments on that?
Sure. Just one point, so over the last decade or so, I've seen quite a few market reports, and those TAMs vary. But when these people speak about what is the e-waste market, it can range from 30 billion a year to 90 billion. But regardless of what it is, they're basically speaking to the intrinsic metal value. So how much metal value, all metal value, is in that e-waste. However, with that said, when you look at the e-waste per pound, the majority of the value from that on a volume basis, first and foremost, comes from gold, the gold content. Secondly, I would say the silver content, and a close third behind is copper. So while there's 24 different metals in electronic waste, the ones that really bear the brunt of the overall intrinsic value, 90% or greater, are pretty much copper, silver, gold, and sometimes palladium. Again, now that varies depending on the electronic waste type. For very low grade material that has very low to no gold value, then you're looking at nearly 100% of the value is basically bulk copper.
That's interesting. I mean, the four main metals, is that really a function of really what's available in terms of making up the mass component of electronic waste? Or are those metals really the sort of key or target metals simply because of ease of use? Is it a little bit of both? Are there other metals within electronic waste that are potentially recoverable, but perhaps not economically so?
Absolutely, that's a good question. So yes, those metals are relatively easy to use, and I state those four metals because typically, if you're an e-waste collector and you're sending your material to a refiner or a smelter overseas, those are pretty much the four metals you're going to get paid for. However, with that said, there are a lot of other bulk volume, so high mass volume metals such as zinc, aluminum, and iron, which are contained in electronic waste. And typically those metals are viewed as low value, sub $1 per pound value, or even much lower than that in the case of iron. So typically people don't even really focus on recovering those. And if they did, they surely wouldn't pay for it. Also, with that said, in the last few years, there's been a pretty big push on some other, what I'll call metals of value. And when I say metals of value, I'm thinking anything that has a per pound value higher than copper. And those metals are things such as tin, nickel, cobalt. Tin, for example, can range anywhere between 1% and 5% by mass in electronic waste. And nickel is typically between the 1% to 2% range, but those metals have values of between $11 and $15 per pound. So there have been a lot of companies out there focusing in the last few years towards those two particular metals pertaining to electronic waste. There are other trace metals like rare earths and metals like that, but really because they're in such low volume, regardless of their value, I think it'd be very difficult in today's technologies to recover those at an economic level.
Oh, that's interesting. Just as you were prefacing that, you were talking about sort of practices where people are sending waste and things like that. I mean, in general, can you sort of compartmentalize or break down sort of the current methodologies in how the vast majority of these wastes are being handled?
Sure. It's one of these things where the old expression goes, if it ain't broke, don't fix it. And what I mean by that is, for decades now, electronic waste, the vast majority of it, regardless of where you are in the world, but especially in the US, majority of it is shipped overseas. And it's shipped to what you call an integrated smelter. The majority of those are in Europe. There are some in Japan as well. There used to be one in Canada, but there are no integrated smelters in the United States. So we're almost kind of forced to ship our material overseas to be processed. Smelting involves pyrometallurgy. So basically just you've got these very, very large furnaces and you throw your material in there. And what it does is it basically burns off any non-metallics. So it'll burn off any plastics or organics you have around. It'll melt down the fiberglass into basically a flux. And then from that, you can separate out your metals. However, one big misconception is people often compare pyrometallurgy, i.e. thermal or smelting, with hydrometallurgy, i.e. water or chemicals. But the fact of the matter is pyrometallurgy in and itself does contain both thermal and chemical processes. So the first step is thermal. You separate out your metals, which is just a big mix of metals. And then it goes into a hydrometallurgical process where you chemically dissolve and separate out those metals. Versus the less common, but making a very big rise in the last decade, are all chemical approaches. So these are approaches which don't thermally manage the material ahead of time. You would just kind of like grind and shred the e-waste into small particles. And then that goes directly, plastics, fiberglass, metals, all go directly into a chemical vat for processing. They both have their advantages and disadvantages, but I would say due to the desire to stop shipping quote unquote waste around the world and new regulations being implemented by governments all over the world, it's inevitable that there will be a time in the near future where we can no longer ship to smelters. So unless you have one in your country, you better find a way to process that material yourself. And that's why there's been a lot of emphasis and a lot of startups around the world who are focused on mostly hydrometallurgical only processes for recovery of metals from electronic waste.
Interesting. So really, essentially, in a nutshell, essentially what we're seeing is, as a market, the moving away from sort of centralized smelters which handle various mixed feeds to more specifically tailored sort of hydrometallurgical processes which really deal with much more specific, let's say, feedstocks. Is that correct?
Correct. Yeah. As I said, there are advantages and disadvantages. One real big advantage of a smelter is they're extremely large, and you can basically throw an entire laptop in there. There's really no need for pre-separation, sorting, and size reduction. You can do that. So they're very, very high volume. But of course, with burning comes a lot of other constraints and things you need to do to handle any off gas and other potential toxins that are going to the atmosphere. Whereas with an all chemical approach, by nature, you're now putting all that waste, all that material into the hydrometallurgical process. So the size of the system might be larger, but it really doesn't have many more limitations. There are challenges, and I wouldn't pick one over the other. I think both these processes, both hydro and pyro, bring their advantages and disadvantages.
Very interesting. I mean, from an industry standpoint, I mean, we were talking a little bit about, the hydrometallurgy, which is I mean, I don't really your area of expertise. I mean, for the viewers quickly, I mean, are we looking at, I mean, in general, how would you describe to a layperson how one of these hydrometallurgical processes work?
I would look at it as you basically take a printed circuit board, for example, and this would be a good time to kind of emphasize this. We talk about electronic waste. Electronic waste in general is, could be defined as anything that contains electrical components inside. So it could be a radio, because that radio has transistors and switches. It can be a laptop, a phone, a TV, anything that has a printed circuit board or electronics. What most people actually process is the actual electronic portion, largely the printed circuit board. So if you take a laptop, for example, the laptop, the 95% of the actual value in that laptop resides on or inside the printed circuit board. The metal, the plastic, the glass, all those make up a very, very small portion of the overall value. So typically, when people collect electronic waste, naturally what they'll do anyway is they'll kind of break it down and disassemble it and then sort into different streams. So the plastic in one stream, the plastic housing, the metal housing, the glass screen in another stream. And then they specifically get to and target the printed circuit board or the switches or the connectors or anything that contains metals. That when we talk about smelting and hydrometallurgy, 95% of the time, that is what people are processing. They're not really wanting to process the large bulk volume plastics, glass, and whatnot. So with that said, they'll take that material, that printed circuit board, and in the case of a pure hydrometallurgical process, they have to kind of break it down to smaller size, because these printed circuit boards range greatly in size and shape. They can be anywhere from 1.5 feet by 1.5 feet in size. They could be as small as 1 inch by 4 inch, or they can just be simply nothing but components, which can be the size of a grain of rice. So in order to homogenize all those variable sizes and shapes, they basically run them through shredders and grinders, and they'll reduce those material down to a uniform size, whether it's millimeter size or micron size. That material now is much more homogeneous and uniform and easier to handle, and that material would then go into a chemical vat. And from there, everything changes. I mean, everybody out there has their own way of doing that. Some people digest everything. Some people digest everything and then selectively pull out one metal from another with various techniques such as electrowinning, ion exchange resin, precipitation. Other people go in and say, we're going to dissolve out selectively one metal from the other. So many, many different approaches. And that's kind of where the differentiation is among all these small startups and companies who are just getting into the hydro portion of e-waste processing over the last 5 or 10 years. That's kind of where they all kind of make their name, if you will.
Interesting. So from what I can take away is that it's very it's highly dependent on the type of feed that's coming in.
Yes.
And the type of feed obviously determines the type of metals that are potentially targets. And so essentially your chemical process is essentially tailor-made to the metals of interest from that particular feed, if I understand correctly.
Absolutely. And just one more thing to add to, I mentioned it briefly earlier, that in a non-smelting or non-pyro process, you do have to handle and deal with the plastics and fiberglass. The one kind of quote unquote good thing about smelting is in the process of smelting, you do separate the metals from the fiberglass into a slag. And then of course you burn off any organics. In hydrometallurgy, you do have to contend with all the plastics and fiberglass that are left over after you extract out all those metals. And that can be anywhere between 50 and 80% of the overall mass of the printed circuit board. So you're now generating or creating very, very high volume, quote unquote, waste streams. So there's been a lot of emphasis, and the real holy grail to an all hydro process will be in the end, not just extraction and recovery of metals from those printed circuit boards, but to find homes and applications for upgrading the plastics and fiberglass so that they're not going into landfills or burned in a formal process in a third world country. There are very few companies out there who are focusing on that, largely because it's hard. So in a way I can understand from a company standpoint, it's all about dollars. So you want to focus and extract out the value and kind of, get rid of everything else and not have to deal with it. Just close your eyes. But the fact of the matter is you can't any longer. If you want to be a responsible recycler and metal processing company, you have to at least, at the very least, find a home or partner with somebody who has interest in those plastics for particular applications, and to do something with them. So again, that's just my opinion, but that's the real differentiation between hydro and pyro. But with that said, as I said, with pyro will never can never be defined as a closed loop process, simply because you're destroying something. You're burning and destroying the organics, which sure, you could actually do it in a manner where you could convert those organics to fuel and to fuel process, but it's never totally circular because you can't put those materials physically into another application. So smelting by definition can really never be closed loop and circular.
Very interesting. I mean, without getting into too much detail or technical detail, proprietary information, and all the rest of it. I mean, I think the first thing when people hear about hydrometallurgy, they're talking about chemicals, and immediately, you know, chemicals evoke some sort of reaction with individuals: dangerous, pollution, toxicity. I mean, in general, how well can these? I mean, first of all, I think from your perspective, is there anything you can comment on in terms of, these processes with respect to their environmental or occupational health and safety liabilities? Are they safe? Are they green? Can they be designed as such? I mean, just a little bit on the notion of chemicals and doing these types of processes.
Sure. There is a misconception, and I think mostly it could probably be better explained as a misunderstanding of chemistry. And when people view chemical processes, they view it as being on a very, very large scale and therefore not economical. I also think there's a misconception out there that chemicals are innately toxic. Well, I use this expression a lot. If you drink too much water in a short period of time, you will die. It will be toxic.
Of course.
So it's not just the chemicals can be defined as like some may have toxicity, others may be completely benign. But in either case, what's more important is how you handle those chemicals. For example, I worked for a former employer who their number one product line was arsine gas, which is incredibly toxic. However, they had a unique technology for storing and transferring the arsine gas where essentially there was zero possibility of ever having an accidental spill or arsine leak. It was a mechanical technology that they used, but because it was very, very safe, they were actually able to ship that product around the world by air, where typically high pressure gases, toxic gases such as arsine, have to go by boat. So you can take a very toxic material, but if you handle it appropriately and manage it appropriately, it's harmless, right? You can take something which is relatively benign, and if you handle it inappropriately, it can be dangerous. So when it comes to hydro processes, obviously as a green chemist, first and foremost, I want to use materials which have low toxicity, first and foremost. And second of all, from an economic standpoint, I want to design chemicals and processes which have chemicals which can be regenerated or recycled back into the process. Not all chemicals can do that. Many chemicals actually decompose upon their use, and that typically makes chemical processes very, very low margin, if economical at all. So again, it just comes into basic common sense and technical creativity to start with materials which are as safe as possible, but also can be generated as much as possible. Furthermore, what people tend to kind of sometimes forget about is in a hydro process, you typically, even in pyro for that matter, you typically use a lot of water. And from my personal experience, typically the largest portion of a chemical process is a wastewater treatment plant, both from OpEx and capital standpoint. So it's best to try to design processes which can minimize the volume of water required, but then also when you do have to treat whatever water you use, finding a way to incorporate that back into the process. And that's what I've spent pretty much my entire career doing, to really design as closed loop as possible systems for recovering metals from all different sorts of waste streams.
Yeah, very, very, very interesting. I mean, I think one of the interesting things, or one of the things that we see when we you jump on the internet, you type in electronic waste recycling, any number of things, pop up. One of which, obviously, there's an enormous amount of information out there, both good and bad, useful and non-useful, accurate and inaccurate. But one of the things, for instance, going on a YouTube video and seeing any number of individuals with these small chemical processes to be able to sort of do recovery of things like that. Really, what you're talking about is incremental, I mean, ginormous steps or enormous steps from, let's say, playing around with vats. Really, what you're talking about is a truly engineered, safe process, which deals with chemicals. It also deals with the rinsing waters, the waste waters, any gases that are generated, and everything is basically compartmentalized and packaged to be sort of a safe, not only safe from but efficient, but also be able to reuse these chemicals, and with complete sort of sound engineering practices, as opposed to what you sort of see on videos with people playing around with open buckets, et cetera, et cetera.
Exactly. Yeah, there is a lot out there. It's interesting where people show on YouTube, dissolving a certain metal in, household, food grade materials like vinegar or citric acid or whatnot. And those are very, very, while accurate, very, very low, low sophisticated, if you will, systems. I mean, they handle one specific thing. And the fact of the matter is, yeah, vinegar is going to be deemed non-toxic, but due to its cost on a high volume basis and the fact that it's only going to recover or extract one particular metal out of 24, there's no way that a system like that would ever be possible. So these hydro systems, as you said, have to be designed and created in a way that they can handle very complex mixtures of metals, not just a specific metal, but dozens of metals, but also in a manner, as I said, which minimizes waste generation, which encloses any off-gassing and recouping it back into the process, which minimizes energy consumption. So ideally having processes that don't need to use hot or heated chemistry, designing chemistry that can be used at near room temperature. That's also a significant savings in both energy cost and sustainability from a sustainability standpoint. So it can get really, really complex. And it's one of these things where that experience comes with time. I've been fortunate in my career to work with many, many different companies and experience firsthand many, many different types of technologies for all kinds of things. Metal recovery, metal digestion, wastewater treatment, et cetera, et cetera. So I've seen firsthand the pros and cons of every type of technology. And there is no single perfect technology. But I've had the ability to kind of look and say, take the best portions and leave behind the bad portions of various different technologies, and then incorporate all those together like a jigsaw puzzle into one process, which overall is what I would deem the best. Is it perfect? No, and that probably doesn't exist. But again, it's being in a position I'm in, it's enabled me to do that, whereas lots of companies will choose a technology for metal extraction or for metal recovery. That's their business model, that's their area of strength, and they will focus on that. And that'll kind of blindside them to anything outside of that isn't good or is competitive and therefore a threat. I don't view things that way. I'm agnostic. I'm technology agnostic. Whatever gets the job done in the safest, most environmental and cost-effective way, that's what I'm going to do.
Yeah, very interesting. For viewers that are basically looking at this and saying, "Hey, I've got an electronic waste somewhere," um, what should they be thinking about in terms of, before they come to a company like emew? What should they be thinking about, or what sort of the questions should they be asking themselves to say, "Is this worth it? Is it not?" Is there any sort of rules of thumb or simple, just to be able to evaluate this sort of quickly, to be able to see if this is something that's worthwhile to them?
That's a great question, and probably the most important question of this call. And I say that because the answer is really supply, supply, supply. So when people say they see volumes and TAMs of 88 million and volumes of 70 million tons of e-waste generated annually, they get into this business saying, okay, there's pretty much going to be an infinite sustainable supply of electronic waste, and so I want to get into that business, right? It's worth a lot. There's a lot of it. Why would I want to get into it? I have seen personally so many companies, both big and small, fail horribly because they basically design a process and hope that the feed will come. And that rarely happens in that way, meaning it's so competitive out there today to get that material that typically it's sold on the open market, and people essentially, like the housing market, get into bidding wars, right? And you quickly find yourself now paying 70, 80, even 90%. I've even seen over 100%, where people have paid over 100% of the metal value for that material to run through their process. Obviously, the more you pay for it, the lower your overall margins are going to be. So there's a threshold where you need to get that material at a certain percentage of its actual value. So there's a big enough gap there to be able to have operating costs and overhead and still make a profit. So yes, I think it's easy for anybody, for the most part, to get their hands on very large sustainable supplies of electronic waste to run a business. The real question is, can they do it in a profitable manner? And lots of times the answer is no. So that's why I would strongly recommend anybody say, tell them, do you have your supply? A, is your supply sustainable? And C, what is the cost of your supply? Typically, I would advise clients to partner with companies who already have those sources, but maybe don't have the ability to actually process, recover those metals. Instead, they're shipping overseas today. So you bring a technology, they bring the supply, which is sustainable and a lower cost. You partner, and it's a win-win. So it's a very, very good question, and I just have to emphasize that again, because I've seen that over and over and over. People want to start processes, and we're going to process 30 million tons a year and put up 100 plants in the next 5 years, only to find out after they spent tens of millions of dollars in capital to build their technical process line for metal recovery, to realize, we're paying 90 cents on a dollar for this feed. So, you're not going to be in business very long.
Yeah, I can fully appreciate that, and it's certainly an interesting one. I mean, it's e-waste. It's widely understood. It's perhaps widely misunderstood, I think, and I
Yes.
think that's perhaps one of the most important things. And I think for any organization that's interested, or any individual that's interested in pursuing this, the resources are out there, the help is there, the technology is available, and it's simply a matter of being able to liaise with the people that have that knowledge base, the expertise, experience implementing these plants, and for them to sort of be walked through this for guidance, and ultimately to be successful in their own e-waste recovery process.
Correct. Yep.
Thank you very much, Michael. I know you're a busy guy, so I won't take too much of your time, but I appreciate the time you did spend with us, talking a little bit about the market in general. And yeah, if our viewers have any questions, I'm sure they can forward them to info@emew.com, and we'll be happy to answer them. Thanks again, Michael. We'll take care.
My pleasure. Thanks. Bye.